Hi, this is Steve, E6WZ. What a great spring day here out at the remote station to tune the 160-meter transmit antenna. Since I built the two-element transmit array here, this winter I was having trouble with arcing in the matching network, and because of that I realized the voltages were too high, and in order to lower the voltages, I've decided to add a second shunt wire to the tower, which will lower the reactance and therefore increase the matching capacitance and lower the voltages found across the capacitors. But while I was out here doing it, I thought, well, why don't I put together a video to describe the method of shunt feeding a tower. You know, there's a lot of information online, but what I discovered was not a lot of detail on actually how you go about setting up a grounded tower for feeding it on, well, 160 meters or 80 or even 40, I suppose. So what I'm going to do while I'm out here is show how I use two different analyzers, the AIM 4170B analyzer as well as the Rig Expert AR55 Zoom. And using those analyzers and doing some experiments actually show how we find what's called the 50 ohm point on the tower. That's what's required if you want to do a single capacitor gamma match. And in doing that, show how moving the tap point higher or lower changes that resistance. I'm also going to show how changing the spacing of the wire closer or further from the tower also affects that measurement. And then, of course, what I'm doing here is show the effect of increasing the wire diameter by adding a second wire and how that greatly changes the reactance, and even talk about the effect of that change on the component ratings. And also show, by making measurements, how the increased wire diameter will change the 2-to-1 SWR bandwidth, which is interesting as well. Anyway, before we do that, let's just go inside briefly and talk about the theory of gamma matching a tower.
So here is a diagram showing the basic anatomy of a shunt-fed tower. We have the tower itself, and most often some kind of top loading, which actually takes the form of the high-frequency antennas, tribanders, monobanders, whatever. And at some point on the tower, we attach a shunt arm, which is usually just a piece of aluminum tubing spaced some distance from the tower, and then what's called gamma wire is connected to that and comes down to the ground, where we have what's called the gamma capacitor. It's a series capacitor which is fed into the center conductor of the coax. The shield of the coax is attached to the ground radial system, or the ground, and that effectively is the anatomy of a shunt-fed tower. The key for gamma matching a grounded tower is to find the 50 ohm real resistance tap point on the tower. And the way we do that, or find that, is using an analyzer connected at the base of the tower between the gamma wire and ground. We'll do a sweep, an analyzer sweep, or take individual data readings at a specific frequency and measure the real resistance at the feed point. And that's always quoted from any analyzer. The diagram shown on the right is from the AIM analyzer, and you can see the 50 ohm point is found here. The frequency is on the x-axis from 1.6 megahertz to 2. So in this instance, the 50 ohm point on this particular sweep is down around 1600 kilohertz. Whereas here in the middle of the 160 meter band, the resistance point is only 36 ohms. Then, once we've found and got the shunt arm at the 50 ohm point, we then will select the gamma capacitor to tune out the inductive reactance of the tower. In all cases, it's required that the reactance be inductive, and in most cases it will be. Most towers loaded with Yagis usually will end up being too long and therefore inductive on 160 meters. In this case, again shown in the diagram, the 50 ohm point is found here, and at that point the inductive reactance is 393 ohms. We can calculate what capacitor will tune out that inductive reactance by using the formula where capacitance is 1 over 2 pi frequency times the inductive reactance, but multiplying by 1,000 will provide a calculation of picofarads. In actual fact, the best approach is to tune it out in the field using a variable capacitor. And quite simply, we tune out that inductive reactance and we're left with a perfect 1-to-1 50 ohm match. Finding the 50 ohm point on a tower is done by understanding the effect of changes to the shunt arm location and the wire location. Here's the way it works. If we move the shunt arm up the tower higher, that will increase the real resistance. If we move the shunt arm down, it will lower the resistance, obviously. If we move the gamma wire closer to the tower, that will lower the R. And if we move the wire further away, that will increase the resistance. And this can be done just moving the wire at the base of the tower, though if we increase the length of the shunt arm as well and move the entire wire further from the tower, that will have the same effect. But the fact is, it's quite easy to fine-tune the tower just by moving the wire closer or further from the base of the tower. It makes it very easy to fine-tune the setting. The question, though, is how do we get an idea, at least, as to where that 50 ohm point will be on our tower? Well, there's just two great monograms and charts which are published in ON4 UN's low band DXing book, the 5th edition, on page 963 and 9-64. This first monogram on the left is used to define and discover the estimated electrical length in degrees of your system. And what we have here are a number of lines which represent different top loading, which are quoted here at the bottom, depending on what type of Yagis you have on the top of your tower. In my case, I have none of these, but I just estimated based on my 80-meter Yagi and small opti beam that perhaps it might be equivalent to something like a 6-element tri-band beam, and that's this finely dotted line. And I know the height of my tower is 28 meters, so 28 meters, we follow it up to the dotted line, and that would suggest that the electrical length of my system might be around 100 degrees. Using the monogram on the right, we then identify our 100-degree electrical length of our system. And then at the bottom, you can see there's two different things to determine either the capacitance that we should expect or the tap height based on the spacing. Okay? In my case, I decided to consider the spacing being 1 meter, in which case it's the broad dashed line, if you'll see here, for the tap point. So you can see that my tap point on the dashed line will be around 20 meters high, and the capacitance with a 1 meter gamma rod spacing would be around 250 picofarads. I'll show that really at the end of the day this is of nominal value in terms of being able to accurately set up your tower, but it's very good to give you a rough idea as to where to start. So let's go back to the field, and I'll describe how I take these measurements, and then we'll come back and actually look at the results.
This is the method I use. Pretty simple for putting mounting the shunt arm onto the tower. Basically, I just hose clamp using worm gears each shunt arm to one of the rungs. I mean, each tower and each installation will be different. What I'm showing here, of course, is when I've added the second shunt wire, so that I have the two to improve the reactance. Basically, it's a 1/2-inch aluminum tubing, and on the end, I've got a quick. I'll just make a quick video of how I've mounted the shunt wire to the end of the shunt arm. Using the AIM 4170B analyzer, I'm going to assume anyone using this device has read the manual and understands how to properly calibrate it. In my case, I've calibrated the analyzer to the end of this short RG58 piece of coax with 2 clip leads on it. And one other trick I've done is I've built a little 12-volt supply out of AA batteries in a battery holder just to enhance the portability of the device and have it connected to my laptop. So the connection to sweep the raw gamma wire is the one lead from the analyzer goes to the actual shunt wire, which goes up to the shunt arm. And the other lead goes to the ground system, okay? It goes to the, in this case, copper wire, which is connected to the ground radial system, which is tied into the tower itself. And by the way, it's essential, of course, to have as good as possible a ground radial system under your tower to maintain transmit efficiency. Perhaps at the end of this video I'll have a quick rundown on the grounded system here. I won't actually do the run here now, but I will effect a number of runs and then show them when we get back to the house and do a different video and showing all the different sweeps. But this is the basic setup using the AIM. Using the zoom, it's 2 different ways you can sweep the gamma wire to measure the real and complex impedance. I use one method is to use the RX graph, which is the shortcut is the number 5 button. Make sure that you've selected your frequency range to cover the band you're interested in. In this case, it's the 160 meter band. Then we press OK to begin the sweep, and you'll see that we do a sweep, and the yellow line is the resistance, and you can see on the graph it's just slightly above 50 ohms. This gives you an idea of if you want to see it across the band as to where you're finding the 50 ohm point. Another method, or the second method which I use, is using all parameters. That's the number 8 button, and then we press OK to begin the measurement. And in this case, you can see what's quoted here in the series model is the real resistance and the reactance for the model. Also, on the series model, it actually shows the series capacitance required of 184 picofarads to tune out that reactance. We'll discuss a different way of tuning out the reactance and measuring it actually in the field. Anyway, that's the method I use. Again, by the way, when you do this sweep, you want to make sure that you've selected the frequency that you're interested in measuring, because that's specific to 1825 kilohertz in this case. This is how I use the zoom. I'm not going to make or show any more measurements using this directly, since I'm mostly going to use the AIM analyzer, because I can save the charts, I can save a graph, and then using the computer review those graphs on the computer at home and make a video. It's going to be much easier to discuss the changing results. So, using the setup I just showed with the analyzer in series with the gamma capacitor variable, we use the zoom when we have it set to the proper frequency. We want to make sure that we're set on the frequency we wish to measure. And then we use the SWR function. And you'll notice that the frequency I have it set to is 1825. And then we press OK to begin the reading on the meter. And then we vary the variable capacitor and tune it for a dip. I find the zoom is really my preferred instrument for doing this adjustment. It's really handy graphical interface and quite convenient. Though you can also use the AIM, and I perhaps we'll show a brief video on how that's done, but this is really far more handy. After we're done this, we then leave the variable capacitor adjusted as is, and using the same zoom analyzer across the leads of the variable, we just measure the set capacitance so we know the approximate component value that we need for the final matching network.
So right now, I'm in the field making this recording, and I have the analyzer connected in series with the variable capacitor, just the way I had with the AR55 zoom, and I'm going to tune out the reactance of this particular wire as we had measured here using the capacitor and measure it with the zoom, or rather with the AIM. We use what's called point data down at the bottom here. And it's important that we select the frequency we want to use, and in this case it's megahertz, 1.825, and we do what's called tune. We select the tune method. In this case you then activate tune, and I use fast repeat. This is over to the right here. And you'll notice it comes as a real handy bar graph at the top. So I'm changing the capacitor right now as we speak. So you can see as I adjust the variable, the SWR bar graph will dip. And I can get it quite finely adjusted. And so that's the method you use. It's it's workable, it's handy. I must say, I still prefer using the zoom. It's a handier device with the SWR meter function. Here's a diagram from the HDX 589 MDPL crank-up tower, just to show a sketch of the installation that I have. So we, in the field, made 3 measurements with all with a 4-foot shunt arm. First measurement we did was one section down from the top, another measurement at the very top, and a third measurement just 1 foot below that shunt arm. And then we did, of course, 3 experiments just varying the distance of the gamma wire from the tower. Literally the wire just dangling down, and we moved it out and then in 3 different positions. And then, of course, we also did a number of sweeps comparing the 1 wire compared to 2 wires, 2 gamma wires, which is effectively increasing the diameter of the shunt wire. So this is our first sweep. So this is a plot from the AIM analyzer, which was saved to the laptop. Along the x-axis is the frequency, 1.6 megahertz on the left and 2 megahertz on the right. And this particular plot, I chose to only show the series resistance and reactance, plot only those 2 parameters, and only the real resistance shows up, since the scale is such that the reactance falls off scale. So the solid line in the middle is with the shunt arm just one section down from the top, and it turns out that fortunately for me ends up being very close to the 50 ohm point, as I have plotted here. Then we move the shunt arm to the very top of the tower. That's the top graph with squares, and that turned out to be 75 ohms, all measured, by the way, at 1825 kilohertz. And then moving the shunt arm just down 2 feet, the resistance ended up being 47 ohms only. So, look, if we do a quick ballpark resistance delta versus height, this would calculate out to be somewhere around 1.5 to 2 ohms per foot. In truth, I'm uncertain that this would be entirely representative of all installations. It might be dependent on the diameter of the tower and other things such as that, but perhaps this could be a guideline for others in terms of approximately how far to experiment moving your shunt arm. One other interesting thing to consider is, with the shunt arm at the top, the impedance, not the impedance, the resistance is 75 ohm. Now, if it so happened that we had a 75 ohm system using 75 ohm coax, if we tuned out the reactance at this point, we'd have a perfect match to a 75 ohm system. But of course, most transmit systems operate at 50 ohms. So, okay, this is varying the wire space from the tower. So if we have the base of the wire only 4 feet from the base, that's the middle curve in circles, we have a perfect 50 ohm resistance. Now, if we move the tower only 3 feet from if we move the wire only 3 feet from the base of the tower, the resistance drops to 42 ohms. And if we move it away from the tower to 5-foot spacing, you'll notice that we've increased the resistance to 54 ohms. So as was explained earlier, you can just move the wire closer or further from the base of the tower and fine-tune to get that 50 ohm point. It's a lot easier than changing the shunt arm length. So, uh, for example, let's calculate what required series gamma capacitor will need to tune out that inductive reactance, which we saw just now, which is 475 ohms. Well, using the formula, capacity is 1 over 2 pi f frequency times the reactance, or times 1,000 for picofarads. We'd get out our calculator and we could calculate that. Or, we could go online and use one of the online calculators, which are much easier. By the way, I'll include this link at the bottom of my YouTube video. So, this particular calculator, let's use kilohertz, and let's calculate it in picofarads. So the inductive reactance that we need here is a 475 ohms of capacitive reactance we require, and 1825. Let's calculate it there on that frequency. We calculate it, and so we get the answer. So 183 picofarad capacitor should tune out that reactance. Well, as we showed in the field, it's quite a bit easier just to use a variable capacitor and do it in the field, and then measure the capacitor and you do it that way. But this is another way to give you an idea of what it ought to be. So here's we did that. This is the SWR plot from the AIM. I've plotted SWR in the red line here, and the 2-to-1 is right in the middle here on the graph. And you'll notice, of course, now that we've included this series 183 picofarad capacitor, we have achieved resonance. We have tuned out the reactance completely. So to the right of the chart, we go to inductive reactance, and to the left, it's a capacitive reactance. But by tuning out the reactance, we've achieved resonance, and we've now got a good match at the chosen frequency. So let's add a second shunt wire. In this case, I showed this in the video, but again, hose clamping a second shunt arm to the rungs of the tower, we end up with about a 4-foot wire spacing, which effectively is increasing the electrical diameter of the gamma wire. And so I've plotted both of those runs. So with the dotted line, of course, that's the single wire, and it shows about 184 kilohertz of 2-to-1 SWR bandwidth. And with the 2-wire shunt feed, we've increased the bandwidth now. We're 127 kilohertz of bandwidth. So that's, pretty decent 43 kilohertz or a 50% increase in the 2-to-1 bandwidth, which I think is perhaps worth the effort to enhance the coverage of on the band. So now what about the reactance, though? And this was my objective all along, which was to try and lower the reactance so that I could improve the survivability and eliminate some of the flashover problems I was having in my matching network. The top curve in solid, that's the single wire, all right? And there at 1825, again, the 50 ohm point with the single wire has a reactance of 476 ohms. Now, as soon as we have the 2-wire installation, you'll notice that the resistance has dropped a little bit, about 5 ohms, but the reactance is significantly decreased. It's only about 284 ohms. So what does that mean? Well, let's calculate some component ratings. So first of all, the current in the gamma capacitor in the matching network, it will be given basically Ohm's law. Current will be the square root of power over the resistance. Well, what is the current going to be delivered into our 50 ohm system? Because of course we're dealing with a 50 ohm system, and at 1500 watts we do the math, and that to be about 5.5 amps delivered to the system. So the voltage across the capacitor is given again by Ohm's law. Voltage is current times resistance. Of course, in this case, the resistance in ohms is actually the reactance. So for the 1-wire example, it's 5.5 ohms. Sorry, 5.5 amps times the 476 ohms of reactance is 2.6 kV. And I think it's highly appropriate to include a safety factor. This is described by others online, and as soon as we have high SWR spikes, for sure, or increased humidity, we want some safety factor here to to eliminate any issues that we might have. So, I would suggest use a safety factor of about 4. So, we should at least have 10 kV of rated components to feel comfortable about using this system. Well, okay, now that we have the 2-wire system, though, 5.5 amps times the decreased reactance of 284 ohms, we're down to 1.6 kV, and using the same safety factor of 4, we've lowered our considered value component ratings to 6.5 kV, which is significantly lower, 50% lower than before. So in my opinion, I'm happy with having done this, because I think now I'm hoping that my flashover problems will be gone.
Over the years, on a number of email reflectors, I've read a number of comments regarding using a crank-up tower for a shunt-fed system, and also comments about RF getting into devices and things on the tower, such as rotors and whatnot, and people suggesting that it could be a problem. What I want to point out is, and perhaps I'd like to dispel those myths. Now, I'm not going to suggest that it may not happen, but what I'd like to point out is I'm speaking from experience of this very same shunt-fed tower being in operation for 18 years, and not just here, but also at the home QTH. Regarding discontinuity issues or concerns on the shunt-fed tower, in this case, this is the US tower, HDX 589 MDPL. And first of all, there's a positive pull-down galvanized steel cable, which runs all the way from the bottom to the top, for one thing. Also, the pulleys are all metal on metal contact, and the tower sections themselves are metal on metal. So lots of opportunity to have electrical redundancy. And for that matter, the cable bundle and the coax is grounded at the top and the bottom. And I'd like to also point out, I've never had any evidence of RFI, as in BCI interference from diode rectification or things like that regarding poor connection on the tower sections. It's just never happened. Regarding RFI in the shack from all of the bundles or damage to anything on the tower, again, for 18 years, there's never, ever been any evidence of RF in the shack. And I have multiple controllers at the top of the tower. My 80 and 40 meter Yagi alone have numerous relays, all fed with Cat5 and driven by controllers in the shack. And the rotor as well is there, and there's been never any evidence of RF getting into the shack through those cables. I also have a security camera, an analog security camera fed with RG6, which resides at the top of the tower. I can watch that camera live while I'm transmitting 1,000 watts into the tower. So again, gosh, I'm not going to suggest it doesn't happen or has never happened to anyone, but I'd like to perhaps add some actual experience to those that might be suggesting it could happen or might happen based on theory. All I can tell you is it hasn't happened either here at the remote or at home.
One thing that I did neglect to mention was a bit of a forewarning about Yagis on the top of a shunt-fed tower, which have insulated elements. This is a photograph of the Cushcraft XM240 Ballon. That's the Cushcraft 40-meter 2-element Yagi, which I had on my tower when shunt feeding it, and it has an insulated driver. But the current Ballon, shown here, or the choke Ballon, of course, the feed line is grounded, and the elements want to become part of the loading for the tower when you're shunt feeding it, and because of that, there will be very high RF current trying to get through this inductive reactance of the choke, and that can cause severe heating. In fact, you could see that the box is melted, and it was only when I was at the tower, I could see evidence of this melting, and then discovered the problem. By the way, there is no question this is because of shunt feeding the tower. It's not from transmitting. This is heavy gauge Teflon coax, and I don't transmit more than a kilowatt, so this is entirely because of the shunt feeding of the tower. It's a very simple fix. On all of my insulated Yagis, have a relay at the feed point, which during transmit on 160 meters are activated and ground the elements to the boom. Regarding the ground system for my tower, at the remote, I removed the gravel from the pad, and around the base of the tower, I have a 3/8 inch copper tubing, which is also connected to ground rods at all four corners. The copper tubing is also bonded with a 2-inch copper strapping to the tower. And there are about 100 radials thereabouts, which extend outwards to the entire perimeter of the gravel pad and are soldered to the copper tubing. There's about 20,000 feet total of 14 gauge copper wire here. The bottom line is you want to do the best you can and provide as good a return RF path from ground to the system as you can. But I encourage you to do whatever you can. And in fact, to that end, the photograph here to the left, this is my home QTH. Where I operated for 17 years. And in fact, you can see my house shown here that the neighbors' houses are very close. In fact, I can physically actually read the label on my neighbor's barbecue sauce. We're so close. It was 60 feet of length along the backyard. The tower is located here with the yellow square, and I just put down as much copper as I could in the backyard. I ran some wires along the back fence, and I even ran a couple along the side of the house and out to the curb, and then one on the other side. Now, I used this system for the 17 years I was at the home QTH, and from using this system, I worked and confirmed 208 DXCC entities on 160 meters. So do whatever you can. Don't feel that you need to be on an acreage. It's not like the antenna won't work without an extensive ground radial system. Just do whatever you can. Well, that's it. I hope this video was a bit helpful for those wanting to install a shunt-fed tower. Don't hesitate to do it. It's a great way to get on, especially 160 meters, since it's pretty hard to get a resonant structure standalone for 160 meters, and turning your tower into a transmit antenna is pretty easy. Anyway, 73. This is Steve, V6WZ.